right. Thank you, everybody else. Thank you, everybody, for coming in again. So for our next speaker, when he was younger, he won multiple Vice State champion titles for swimming. Now he's here to win you over with his talk, What's Next for WebAssembly on the Server. Everybody, please welcome Harry Kimpel.
Hello, everyone. The swimming was many years ago, but I still don't drown, so that should be fine. I want to talk to you about WebAssembly, what's next for WebAssembly on the server side, and how to see it in action, kind of like the observability aspect. A little bit about me. My name is Harry Kimpel. As you can tell from my accent, I'm not American. I'm basically living in this part of the world, which is southern Germany, right at the border of Austria, basically. I have been a passionate software developer for basically all my professional career, starting in the Microsoft developer ecosystem. Don't judge me for that, but I started like in Visual Basic 3 and Visual Basic 4, so many years ago. Anyways, I'm with New Relic, which is an observability platform since 2017. And if I'm not in front of a computer, I like all the things outdoors. I mean, it looks very similar to the scenery here, so I very much enjoy that with my family. And this is also my skiing area there, but the skiing season just ended last weekend. Anyways, just on a side note, I just recently asked ChatGPT on, based on what you know about me, draw a picture of what you think my current life looks like. You may know that ChatGPT has a memory function that remembers like the interactions and the prompts that you sent in. This is the response that I received. Here's an illustration capturing your developer life and blah, 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 inspired by the Bavarian Alps. And the picture that I got was this, and I thought this was amazing. I mean, it looks really beautiful, like with all the mountains behind the scenes and my home office. The only thing that my little daughter, she asked me like, how does ChatGPT know that you have so many monitors at home, right? And I'm like, I don't know, maybe it's hallucinating, but I like it, the fact that it also draws some observability, like, images on the monitors, which is, I think, amazing. And then lastly, recently, Kevin Weil, the CPO of OpenAI, they announced this on LinkedIn that they are now able to create photorealistic images when you generate these pictures. And I did the same exercise again, and this is what the result was. Looks really much more polished, right? Almost like photorealistic, like all the mountains in the back and stuff. No more monitors, but anyways, I just thought this was interesting. Let's start with like some of the topic here, WebAssembly, or in short, Wasm on the server side. A little bit about the history. WebAssembly initially was released in 2017 to meet like new performance workloads on the web. Computational tasks like 3D applications and audio and video software, games. Basically, the idea was to run this purely in the browser. And solving issues like other attempts ran into, like anyone remember Java applets or Flash or something even worse like Microsoft Silverlight? These were all like plugins for the browser that you could use. I actually did some development on Microsoft Silverlight, and I'm so glad this time is over. WebAssembly is in W3C standard, official language of the web, and so on and so forth. The point I wanted to highlight here is the focus on running in the browser. That was the initial focus, right? And kind of like the design goals that it had was like fast, predictable, near-native execution, one of the design goals. The second, it should focus on safe, designed for efficient, secure verification. It kind of like everything runs in a sandbox in the browser and very restricted from the capabilities that it can access from there. So that was also one of the aspects. And besides like all the other applets and Java applets and Microsoft Silverlight that I just mentioned. Then the third one, hardware independent. Basically, it should run anywhere and also with any language. You can write WebAssembly in a lot of different languages that you can use. And this is kind of like, these are all the design goals. And then the WebAssembly system interface came into play. Like in 2019, it realized the Wasm design goals could also benefit the server side, right? The same aspect, like having highly computational tasks executed safely and securely in a sandbox environment. And WASI really defines an interface that you can use to interact with your WebAssembly applications and runtimes to your operating system. So it opens up some, defined interfaces that you can use to, have, share memory, share, resources, share data, and so on. And the focus was, to communicate with an OS and run outside of the web. And the thing that I wanted to highlight here in this case is like it was designed to use these design goals, but for the server side, and not necessarily only in the browser. This is a quote from Solomon Hykes, the founder of Docker, and he said, like, if Wasm and WASI existed in 2008, we wouldn't have needed to create Docker in the first place. That's how important it is. WebAssembly on the server is the future of computing. I mean, this is a little bit, hype probably term, but the point is that he tries to make maybe Docker wouldn't even be necessary to implement and create in order to run applications in a container. So what about Wasm outside the browser on the server side? It basically needs a runtime. So whenever you build your WebAssembly applications and you run them, you need to run them. This is basically bytecode. You transform them into bytecode, but they need a runtime to actually execute. And one of the runtimes, I brought a couple examples here with me for the Wasm runtimes is Docker and Wasm. There was this technical preview in 2022. And basically, from Docker desktop in this example, you can basically use some examples here that you can define your Docker files and your Docker containers based on these runtimes. So, there's a containerd implementation for Spin, for Wasm Edge, Wasm time. We get into some of the details for some of these runtimes itself as well in a second. But you have an option when you build your Docker containers. You have various kinds of runtimes that you can use alongside with your Docker containers. So how could that look like? I have this really complicated example written in Rust here. It just prints out like a line here. Then the Docker file for this specific example looks like this. I have a from scratch, and this is one of the first things. I'm not using an operating system like I'm defining in Ubuntu or CentOS or whatever as a starting point for my application. I basically literally start from scratch. And then I copy in my Wasm file, and then the entry point for my Docker container is then the Wasm file, the WebAssembly file that I copied into it. So really straightforward, right? I mean, it's nice to define this, and I probably have a lot of benefit, we'll get to this later, from using such a Docker file like this and not having an operating system as part of it. And so if I then run this, you'll notice that I'm defining in the Docker run command the platform. So I'm using WASI, Wasm32, and then I'm also able to define the runtime for this specific application. And in this case, I'm using containerd Wasm time as my runtime. And you can see the output, hello, LambdaConf 2025. So really straightforward. I can easily create these Docker containers and get them up and running and basically run them anywhere. The second is a runtime called Spin. And Spin is basically a developer tool for building WebAssembly microservices and web applications. It is a runtime that you can use to actually build, not only run your WebAssembly files, but also build them with the. They have a Spin CLI available that you can use to, in this case, use it to create a new application. Then they have a couple templates that you can choose from. Then you can build your application, and then you can say spin up. Then this will then start up the application locally on your machine or wherever you run it, and then execute this using the Spin runtime. What's interesting in this approach for Spin and Wasm WebAssembly is that they also come with this component, which is part of the CNCF Foundation now, called Spin Cube. This actually allows you to run your WebAssembly files as part of your Kubernetes environment. So there's dedicated runtimes and operators that actually run alongside your Kubernetes cluster, and then you can point your Spin WebAssembly applications to use these runtimes specifically in your Kubernetes environment. So really interesting project, and in my opinion, it solves a couple of challenges because not everyone wants to run Kubernetes workloads, but basically if that is what your architecture looks like, then this is probably like a good approach here. The next one is a runtime called Wasm Cloud. It's basically also an open source project, also part of the CNCF Foundation, and it helps you, build, applications composed of reusable Wasm components, and you can then also run them across clouds, Kubernetes, data center, and so on. This also comes with, interestingly, with a CLI that you can use to actually create Wasm applications based on Wasm Cloud. You can then do something like wash dev to build your applications, run them locally, spin up like an entire Wasm Cloud environment if you want to, in your premises, in your targeted infrastructure of choice, or you can, of course, also run them in the cloud anywhere. And this is also what they do, behind the scenes. Cosmonic is the company behind Wasm Cloud. They kind of like invented this environment. And what they do, they also provide a platform that adds some additional enterprise features on top of Wasm Cloud if you want to use that. So really also quite an interesting environment. The next one is Wasm Time. It focuses on fast, secure runtime for WebAssembly. This is not part of the CNCF Foundation, but part of the Bytecode Alliance, which is kind of like the WebAssembly Alliance that focuses on some aspects there, also from the WebAssembly system interface. And they have mentioned a couple of features here. It is basically built on top of a optimized crane lift code generator to quickly generate highly efficient machine code at runtime or ahead of time. And what's interesting here is that, like all the others as well, they support multiple languages. So they have support for, Rust and C, C++, and Python. And they also come with SDKs that you can use to actually build them into your environment. And one of the interesting aspects here is, this is another example. This is, again, an application written in .NET. But basically, what I wanted to highlight here is that this is a simple console application. It's this thing called I can use the SDK to actually ingest a so-called WET file, which is a WebAssembly text format file that I can use to ingest this into my application and do some executions from within my application and call into WebAssembly. The WET file basically looks similar like this. If you've been to the previous talk on WebAssembly and NOC, they also explained about this. But basically, this is a human-readable format for bytecode. Remember, bytecode, if you compile it, will be transferred into WebAssembly will be converted into bytecode. And this is a human-readable format that you can use. And it's basically the WebAssembly text format. And the benefit there is, of course, that I can see what is happening. I can use it for testing purposes. I can easily edit that code itself, and I can also debug it. If that is kind of like an aspect that I have to focus on, that I can easily use that. And why would we write it in compilation in WebAssembly text format? Exactly what I just mentioned. It is probably not something good for production because the performance isn't good enough. But for experimentation, for development, for testing, QA, this is probably a nice way. And there's also ways in how you can convert the WebAssembly text format into actually WebAssembly bytecode as well. And of course, Golem is also a platform that you can use to deploy your WebAssembly applications on. It is an open source serverless computing platform, and it helps you orchestrate and execute any software packaged into WebAssembly components. All right, so we talked a little bit about a couple of different runtimes that you can use to actually run your WebAssembly applications. But why is it even interesting? Why should we even focus on running WebAssembly on the server side, right? In the browser, yes, it's understandable. You need to have like a sandbox that you can use to actually run your applications. But why on the server side? Why is that interesting? And there's a couple aspects that I wanted to highlight here. Why Wasm on the server? And the first is the performance aspect. So there was a lot of research out there, and I mentioned the source of this here as well, where they did like a single-threaded application, and benchmarked them against like a native x86 application that was compiled into like a native application. And the point is, in this specific example, Wasm was only 14% slower, which is close to near native performance. The reason why it was a little slower than the native x86 application is, of course, you have to have a Wasm WebAssembly runtime that you need to use, and it adds a little bit of overhead. But still quite good. I mean, the benefits are, you can run it anywhere. You don't have to rely on this architecture, and you can also write it in any language. The next aspect is, and this is another research that they did, they ran a simple application reading a file and perform some actions on the file. The Wasm runtime in this case was at least 10% faster than a Docker running the same application from cold start, which is another aspect that is really important, specifically when it comes to containers. And it's in other examples, I mean, not looking specifically at the simple application reading a file and performing some actions, they found out that usually WebAssembly performed 10 to 50% faster than the same app containerized, even if it's not being like from a cold start, but if it actually was warm and could have executed directly. So also really interesting aspect from a performance perspective for WebAssembly. And lastly, the other aspect in traditional Docker versus Wasm container aspects, they also did like a simple HTTP server and things like that. And interestingly, for this specific application and for this specific use case, where they used like a simple HTTP server that was executing some task and did some load testing on it, interestingly, WebAssembly applications showed a worst case latency of about 15 seconds, whereas the Docker containers had a worst case latency of 0.8 something seconds. Why is that the case? Well, the reason is kind of like from a Docker perspective, you can easily set up new containers. You can actually spin up and deploy this, and it is not necessarily focused on a single threading application. This is kind of like still some caveat when it comes to WebAssembly. But of course, maybe with WebAssembly, you don't need to scale this in a multi-threaded environment. Maybe it just makes sense to even use additional WebAssembly instances that you start from cold, right? And rather than having a multi-threaded focus for these applications when it comes to comparison with Docker containers. And this is also what I mentioned here, lack of support for multi-threading Docker containers when stressed increased the CPU utilization, and Wasm, due to its current single-threaded nature, only utilized a single core for this. And then talking about the cold starts. So WebAssembly, the threading proposal is still in the works, so that may be something that we are looking into. But with a slightly modern setup, you can use the cold start time from WebAssembly was about 160% faster than that of a Docker container, which is impressive if you think about, if you want to use Docker containers and spin them up, spin them down, especially like in a highly dynamic application where you start instances up and down and scale broad, then of course this is a key aspect. And when you compare this with like WebAssembly, and you can more easily and more faster use these cold start scenarios to actually get your applications up and running and ready to deliver whatever it is focusing on, it has a huge benefit from running this. And then lastly, another benefit when it comes to why WebAssembly on the server is the aspect of density. There's this company in Germany called Zeiss. You may have heard about them, when you think of your glasses. They produce like these, the glasses, telescopes and things like that. So they are a really old company that was always focusing on this, and they do some really interesting things these days. And one of the things that they did is they compared like a Node.js Express application and just compared it from a deployment size of the environment, and compared the Docker containers compared to like a WebAssembly. And the numbers are really interesting because they came down from 423 megabyte of a single application, like from a sizing perspective, to like 2.4 megabyte for WebAssembly, which is of course interesting if you run your application in a Kubernetes cluster, for example, again, and you only have certain types of resources for your nodes and for your storage and so on and so forth. Of course, the size of the container makes a huge difference when it comes to that. So you can basically save on resources in your cloud environment or in your deployment environment of choice. They also did this a session on KubeCon last year where they actually talked about it in detail, and the link brings you to the actual YouTube video. So then the last question is, using WebAssembly on the server side is great, right? We still want to know what is going on with our application. So if you want to observe our applications, monitor our services, why are certain services slow or expand or generate some errors and issues, we want to find out all the things about the applications in general. And a nice project, who has heard of OpenTelemetry before? Okay, so maybe half of it. This is really an interesting project in my opinion. I mean, I work for New Relic, and we have kind of like, our founder has kind of like invented that space of application performance monitoring. And of course, we had our own APM agents that you can attach to your applications and servers and containers, and they would analyze what is happening inside of your application. But of course, our agents are very proprietary. They only work with our platform. And this is really where OpenTelemetry comes into play. It's an open standard, now also part of the CNCF Foundation, where it's really kind of like a merger. It started as a merger of two different projects, Open Tracing and Open Census, focusing on tracing or rather metrics. And OpenTelemetry really wants to combine all the different telemetry, all the signals from your applications and infrastructure into a single standard. So typically you would see things like traces, metrics, and logs from your applications. And OpenTelemetry allows you to collect these and then process them in an open, vendor-agnostic way. What's also nice about this is that it comes with an environment like this OpenTelemetry collector pipeline. And you can think of this as like a real pipeline in the sense of, I have at some point for you on the left-hand side, my applications written in all the various languages in Rust and C and C++ and Java and Go. You can then point the telemetry that is captured from these applications into this OpenTelemetry collector pipeline. Of course, you can also use some receiving functions to get data from your cloud vendors, from your services, from your Prometheus environments, or from other services, which will also be able to ingest them into this pipeline. And then as a second step, you can then also process the data directly as part of this pipeline. This entire OpenTelemetry collector will typically run alongside your applications where you collect the data. And of course, then you can also do some processing on the data that you collected. For example, one of the examples that I always use is one of my developers, they choose to send in some debug logs, which could be nice for debugging, but not sending them off to some OpenTelemetry backend. In this case, you can drop these directly. You can choose to drop them and not forward them anywhere at all. Or some examples on, hey, I captured some data that I shouldn't forward to any other system. That could be like credit card information, personal identifiable information. And you could then, for example, obfuscate or decorate that data, encrypt that type of data directly as part of this OpenTelemetry collector, so that the last step, the exporting function, where you then send off the data to some observability backend, will not be visible in readable format. And of course, this is also the last step, the exporting. You can then choose what do you want to do with all the data that you collected. You can say the traces I want to send in off to some open source tooling like Jaeger, the metrics to some other system, Prometheus, Grafana, or you can choose a full observability backend that supports all the different kinds of data and probably, of course, comes with a lot of benefits, but you have the full choice of what do you want to do with the data. And of course, you can also use multiple destinations from there. You could send it off to multiple different locations and then, for example, do some evaluation and processing. But this pipeline is really interesting because it comes with all these benefits, and then you can then choose, okay, I want the data then off for some long-term storage and send it off to a backend. So what does it mean from a WebAssembly perspective? So for Wasm Cloud, in this specific case, and OpenTelemetry, if you use Wasm Cloud and to deploy your WebAssembly applications, they support OpenTelemetry out of the box. You can basically enable this as part of the environment. So you can, by default, these kind of things are not enabled, so all the signals will not be captured. But if you enable the Wasm Cloud observability enabled and set it to true, you will then be able to capture this telemetry from your applications and services. And then typically what happens is, then this is the bottom section here, that you would use one configuration parameter like this. This is standard OpenTelemetry configuration. There's one that you can define as an OTel exporter OTLP endpoint. This is kind of like, if you remember the pipeline, the exporting function, you can then point it to some kind of backend. We at New Relic, we support OpenTelemetry line protocol or OTLP out of the box, so you could send the data directly to them or to any other observability backend of your choice. And like I mentioned, if you want to even split it, like sending the traces to some environment and the metrics and the logs somewhere else, you can also do that. But basically, just by these two configuration parameters, you are able then to send off the data and your signals from your WebAssembly applications and then send them off to like a backend where you can then analyze what is going on and identify any anomalies, some patterns, and maybe also some exceptions that you may have captured from your applications and services. And then, this is how it typically looks like. This is a screenshot from within our New Relic platform, but in other systems, it looks very much similar. So you have, in this case, a scatter shot that shows you all the requests from a tracing perspective, where you can then see, where did I see any slow executions, some slow traces, if I had some interactions from one WebAssembly application to another, to maybe a database or to some external service. You can then see this in this chart here, or focus on a single trace to look at what was going on. Did I see any slow execution, or why was, in this case, this is all slow, very fast, but there's one that took like 4.6 seconds to execute. Why was it slow? And especially if you have like a chain of WebAssemblies that talk to each other, you can then directly see, okay, 4.6 is the total execution, and how does it break down into the different sections from there. And this is kind of like one of the views that you can then also see to see that breakdown. In this case, it was almost 4.6 seconds, and then how does it break down into different sections. Spin and OpenTelemetry, they have a slightly different approach. So the Spin runtime for WebAssembly, they focus on an aspect that is called of course, only focusing on Microsoft .NET or C# in this case, but they have this open source project called the Aspire dashboard, and this is kind of like an environment where you can then use this to run the OpenTelemetry collector locally as you develop your applications. So this is really great for development, for testing. You can spin up this .NET Aspire dashboard locally, and all the telemetry from your services will be sent then off to this dashboard that runs locally on your Mac or on your machine that you use for development. And then you can analyze the data directly on your local machine. You look at all the traces, look at some exceptions that may have occurred, and you have all the telemetry in a single platform as part of this Aspire dashboard. And of course, there's different types of so-called instrumentation, and Spin in this case specifically focuses on the automated instrumentation. Typically, when it comes to OpenTelemetry, you have, like, on the one hand, an aspect from a automated or zero code instrumentation, which means that you can attach an agent, like an OpenTelemetry agent, based on your language alongside your WebAssembly. And this will then analyze all the bytecode automatically for you. You don't need to change your source code. You don't need to add any dependencies to your application, which of course is something then you need to manage and keep up to date, and if there's any security issues, and so on and so forth. And also there's, of course, with OpenTelemetry also the aspect of manual instrumentation, where you can then choose the level of detail, the depth of telemetry that you want to capture. If you want to create some custom traces, some custom spans of your application, or maybe create your own custom metrics for your specific use case, you can then do that. But the caveat is that, of course, you need to add in some dependencies to your application. You need to change maybe some source code. Maybe you add some, couple lines of code to create your custom metric, or also have an aspect of where you can then add in some custom attributes for your applications. I typically use the example of like a retail scenario where your end users put things into the cart, and sometimes it fails. And maybe if you see like 1,000 exceptions in the last hour, how do you know that all of the 1,000 exceptions were coming from a single user, or from a single product, or from a single product ID that your users put into the cart? Or is the distribution of errors across all the different attributes, like your products? And this is, of course, one way to easily troubleshoot and find the root cause of an issue if you have like an indication of your exceptions are only coming from like a single product, and for some reason something is going on. It helps you troubleshoot and do some root cause analysis. And again, also for Spin, you will notice it also uses the OTel exporter OTLP endpoint as a configuration. This is really standard OpenTelemetry conventions that you can then use and send the data off to some backend of your choice. How they do that in Spin, I mentioned the Spin CLI that you can use to create and deploy your applications, run them locally, and they come with a really interesting concept here. They have this concept of plugins that you can use, and in this case, you would use an OTel plugin that you can use alongside your application. And then there's different kinds of observability stacks that you can use. The default one is one that accepts OTLP, OpenTelemetry Line Protocol data, or the other aspect where you can send the data off to your Aspire dashboard. So how does it look like? You would first install, of course, your plugins. You can run an install Spin plugins update, and then Spin plugins install the OTel plugin for your application. And then if you want to use Aspire, you can use the Spin command, Spin OTel setup Aspire, which will basically, what happens behind the scene, it will create this OpenTelemetry collector pipeline behind the scenes as part of the Aspire dashboard. I can then build my application using Spin build, and then the command for to get the application up and running looks a little bit different. We used to see like a spin up previously as in a command that you can use. But if you use Spin OTel up, which will leverage the OTel plugin, this will then enable and trigger all the telemetry that you can then capture, and again use the OpenTelemetry conventions like the environment variable, like if you define this as an environment variable, the OTel exporter OTLP endpoint, and to define where the telemetry should go, you can then analyze what is happening inside of your applications quite easily. So in summary, what we looked at is a little bit of the history and the definitions of WebAssembly, the design goals, and the Wasm runtime. We also looked at various kinds of Wasm runtimes like Docker and Wasm, Spin, SpinQ, Wasm Cloud, Wasm Time. There's a ton of more runtimes. I mean, this is just some examples that I used here, and of course also Golem as a way of running your applications or WebAssembly applications in the cloud. The why did we even think about considering WebAssembly on the server? I hope I was able to show you a couple aspects of the performance, the cold starts, and the density, which really make a huge benefit when it comes to WebAssembly applications on the server. Should you always use WebAssembly and only develop in WebAssembly from now on? Probably not. This depends on the use case. But if it makes sense, and some of these aspects are important to you, like performance or density, or the cold start aspects where you want to spin up applications quickly without doing multi-threading, this is of course something you can look into. And then of course, from an observability perspective, OpenTelemetry is really here to stay. I think this is the future. In my personal opinion, all of the agents that are coming from us or from other vendors, they will at some point go away, and we will all use OpenTelemetry. They still have some differences when it comes to features and capabilities, but I think this is just a matter of time until OpenTelemetry is at the same level, and you can use that in various kinds of environments. Wasm Cloud and Spin, showed you a couple different examples on how to use OpenTelemetry in these environments. One example was Wasm Cloud, and the other one was Spin, on how you can use them. And the same also applies specifically for Spin on when you use Spin Cube on a Kubernetes cluster. You can then also capture all the telemetry from within your, from the infrastructure perspective of your Kubernetes cluster, but also, of course, from your WebAssembly applications that run as part of your Kubernetes environment. And with that, that is what I had brought to you for you today. If you want to connect, this is my link to my LinkedIn. You'll probably find me on all the various social media, but I'm also open for any questions you may have.
Any questions? All right, no questions. Thank you very much, Harry. Really appreciate you coming down.
Thank you.